as it were, radial symmetry, which enabled them to radiate in certain ways. The insects have a property, or the arthropods have a property, segmentation, which enabled them to radiate in certain ways. I think that's so different from group selection.
Yeah, it doesn't impose any requirements on individuals or populations to work against their own self-interest.
Precisely.
Yes.
Precisely.
So it's entirely compatible.
So we're not talking about individuals sacrificing themselves for the good of the echinoderms. I mean, it doesn't. That's not what it's about at all.
No.
But then we could sort of ask, well, what are the embryological features which are evolvable? What about symmetry, for example? I mean, bilateral symmetry, five-way symmetry, as in starfish, radiolaria. There are rules of symmetry which are sort of built into the embryology, and such that when a mutation happens which might or might not be selected in ordinary neo-Darwinian selection, if we're talking about a five-way symmetrical starfish,
yes,
a mutation that changes one arm is going to change all five in the same way.
Right.
Normally, so it's like a kaleidoscope. It's something happens all around the radial symmetry, and in a bilaterally symmetrical animal, a mutation that affects the third leg from the front on the right-hand side is going to affect not always, but that would be the general rule.
Yeah, and another way to think of it is that we kind of put ourselves in these Darwinian straitjackets, because now you've got this radial symmetry, and if you're under conditions where, for instance, fast-forward movement is at a premium, the bilateral animals are going to have a natural advantage, and it's going to take extra work for an echinoderm to tweak itself so that it can...
That's right. I mean, extra work is a very good phrase, because it's not impossible. It could happen, but by the time the echinoderms have sort of got themselves together to do it, some bilaterally symmetrical phylum will have done it first.
Yes, or have done it better.
Or done it better. Yeah. Okay. So I think you're not supporting group selection in the sort of Wynne-Edwards, or indeed...
I think we've got a foundation in neo-Darwinian theory that is pretty sound. Okay, if we're going to add things to that theory, they can't really contradict the foundation that we've already got. So in that sense, any theory that comes along is going to challenge some of the concepts that come out of neo-Darwinian theory. It's going to be like those echinoderms. It's got something really working against it for that particular strategy. So yeah, I think any idea of group selection or clade selection has to accommodate itself to the existing body of evidence.
Okay.
And that's sometimes hard to do.
Well, I'd like to pursue your point about what's difficult to evolve. If you think about any animal as sitting in a sort of mathematical, multidimensional space where it could move in all sorts of directions. I'm talking about in evolutionary time now. I suppose that there are some. I mean, it's, for example, lengthening the horns, or lengthening the legs, or shortening the tail, or all the different dimensions of evolutionary movement. And so evolution then would consist of a trajectory through multidimensional space. But it could be that there are certain directions which are resistant. There are certain let's call it a multidimensional museum with cases filled with all possible animals, and you walk along this corridor and you see the horns getting longer. You walk along that corridor and you see the coat getting blacker, and there are any number of these corridors. There will be some corridors which are sort of blocked off, or not totally blocked off, but hard to traverse.
Yes.
For some particular group, whereas other corridors may be so easy that it's almost, you could say, they're kind of eager to evolve in certain directions. Would that be fair, do you think?
Right, and also that You know, in your imaginary corridor, where, for instance, horns are getting longer, the example that comes to mind is scarab beetles.
Yes,
where what
good.
they found is that, you know, you look at scarab beetles and you get this huge range of variation in the horns. You know, some species have none at all, some have huge horns. And when you look at the development of individuals in those species, what you find is that there are some interesting allometric relationships between the tissues, right? So if you, so one constraint is you can't grow a horn infinitely large because it is taking resources from other tissues of the body. And the example in various experiments is, you know, if you enlarge the horns, you get reduced testes size, and if you cut the horns off, the testes grow huge. So there's a kind of seesaw going on right there.
Yes. Perhaps we ought to clarify these seesaws, these relationships between growth in different parts of the body. Those could be fundamentally part of the embryology. You just cannot grow larger horns without the testes getting smaller. Or they could be selective effects that say resources that get put into the horns have to be stolen from Peter to pay Paul. Have to be, and that's a selective effect. I suppose the thing we missed out when talking about evolution of evolvability, it's not just that some phyla might be better at evolving than others, but that there really is a kind of evolutionary effect whereby phyla get better at evolving as the maybe tens of millions of years go by. And that's a novel way of looking at things. That's not a very Darwinian way of looking at things. It's not just that individuals get better at surviving and reproducing, which we're all familiar with. It's that classes, orders, phyla, get better at evolving as the much larger time scales go by.
Yes.
Because whenever a new embryological trick is discovered, which may or may not, and presumably it has to improve individual survival, but that's not what we're talking about now. It not only improves individual survival, down the line, it improves the evolvability of descendants, distant descendants.
Right.
So when the first segmented arthropod, some kind of homeotic mutant, maybe before that there was only one segment and then there were two. Maybe the first segmented arthropod was not that great at surviving as an individual, but its descendants were very good at evolving. Is that possible, do you think?
Yes, although, you know, with that example, I'm actually thinking of arguing against evolvability, which feels horrible. But the other phenomenon going on there is that this may be an epiphenomenon, that what you see when you look at the development of organisms is you see this incredible amount of redundancy. That what's going on in a population is that, of course, what you want to do is you want your offspring to grow up reliably, right? So there's selection for added levels of control to make sure that everything's more and more robust. But that's got the interesting side effect that what you're doing is you're adding all these control mechanisms, things are getting more and more complicated over time, all to guarantee this reliability, but all those different bits and pieces also become new parts of the toolbox.
Yeah.
So that downstream, what you find, you know, many generations later, is you've got this rich repertoire of molecules bouncing around in embryology that can then be co-opted and go off in different directions. So you're not really selecting for evolvability. You're selecting for robustness, which has the side effect of opening up new channels for evolvability.
That's very interesting. Yeah.
Yeah.
Okay.